The art of searching, mastering search algorithms in modern computing. In the ever-evolving landscape of computer science, search algorithms stand as fundamental pillars that underpin everything from web searches to database queries. These algorithms are essential tools that enable efficient information retrieval across vast datasets. Understanding the nuances of different search techniques is crucial for developers aiming to optimize performance in their applications. Whether you're navigating through an array or traversing complex graphs, selecting the right algorithm can significantly impact your system's efficiency. Fundamental concepts of search algorithms operate by systematically exploring data structures to locate desired elements. The primary goal of any search algorithm is to minimize time complexity while ensuring accurate results. Different types of search algorithms exist based on whether they work on sorted or unsorted data. Linear search scans each element sequentially until finding a match, making it suitable for small datasets but inefficient for larger ones. Breadth-first search, BFS, and depth-first search, DFS, commonly used in graph traversal, represent another category of search algorithms that explore nodes level by level or down paths respectively. Linear search, best suited for small arrays where simplicity outweighs speed considerations. Binary search requires pre-sorted input and operates by repeatedly dividing the dataset in half. Efficiency metrics in search algorithms. Evaluating search algorithms involves understanding both time and space complexities. Time complexity measures how execution time grows relative to input size, typically expressed using big O notation. Space complexity refers to additional memory requirements during computation. While some algorithms may offer faster runtimes, they might consume significant extra memory resources. For instance, linear search has O(n) time complexity but minimal overhead since it doesn't require extra storage beyond basic variables. Conversely, binary search exhibits logarithmic growth, O log n, but necessitates maintaining sorted order within the data structure beforehand. Common types of search algorithms. The choice between various search methods depends heavily on application context and data characteristics. Some widely implemented approaches include sequential searches, divide-and-conquer strategies, and heuristic-based solutions. Sequential search methodologies traverse items one at a time without skipping elements, an approach ideal when dealing with unordered collections or when frequent insertions/deletions occur frequently. Divide-and-conquer algorithms break problems into smaller subproblems recursively before solving them individually. This paradigm forms the basis for many advanced searching techniques, including binary search itself. Hash tables utilize hashing functions to map keys directly onto positions within arrays, allowing constant time lookups under optimal conditions. Tree structures organize strings hierarchically so pattern matching becomes highly efficient, especially useful for autocomplete features found in modern interfaces. Applications across various domains. Search algorithms find applicability far beyond traditional software development contexts. From artificial intelligence research projects involving pathfinding challenges to bioinformatics analyses requiring genome sequencing comparisons, these techniques play pivotal roles everywhere. In AI domains particularly, a * algorithm combines best first search principles with heuristics estimation models, enabling effective navigation through unknown terrains represented as weighted graphs. Within e-commerce platforms too, recommendation engines employ collaborative filtering mechanisms which essentially perform sophisticated form of item-to-item similarity searches over massive user preference databases. Moreover, Internet search engines rely extensively upon inverted index implementations coupled with PageRank computations, all rooted deeply within foundational search theory principles. Performance analysis techniques. To determine effectiveness accurately, benchmarking frameworks must be established against standardized test cases covering diverse scenarios. Comparisons should consider worst case, average case, and best case performances separately. Empirical testing provides concrete measurements regarding actual runtime behaviors, whereas theoretical analysis helps predict scalability patterns independent of hardware specifics. Visualizing performance curves often reveals critical inflection points, indicating transitions between dominant algorithmic regimes depending on dataset sizes involved. Profiling tools assist developers identify bottlenecks related specifically either to computational steps taken or auxiliary memory allocations made throughout processing cycles. Optimization strategies for enhanced performance. Improving existing search implementations requires careful consideration towards reducing redundant operations wherever possible. Caching frequently accessed results represents one such optimization technique applicable broadly across numerous situations. Prefetching mechanisms anticipate upcoming requests, thereby minimizing latency experienced due waiting periods associated with fetching new data elements freshly from disk storage mediums. Parallelization offers potential gains, especially when handling very large-scale distributed systems, although care must be taken managing concurrency issues arising from simultaneous access attempts. Certain domain-specific optimizations leverage knowledge about expected distributions inherent within target datasets themselves, thus allowing tailored adaptations better aligned with real-world usage patterns observed historically. Emerging trends shaping future developments. As computing landscapes evolve continuously, novel paradigms emerge challenging conventional wisdom surrounding what constitutes optimal practices today. Quantum computing promises revolutionary changes, potentially redefining entire classes previously considered computationally hard. Approximate nearest neighbor search algorithms gain traction amidst growing demands for fast approximate answers rather than exact matches, particularly relevant within high-dimensional feature spaces encountered regularly nowadays. Machine learning integration introduces self-adaptive systems capable of adjusting internal parameters dynamically according to changing environmental factors, influencing query characteristics over time spans measured in months or even years. Blockchain technologies pose interesting questions concerning privacy-preserving search capabilities wherein confidential data remains protected yet searchable simultaneously. An area ripe for further exploration, combining cryptographic innovations alongside classical indexing schemes. Conclusion: mastering search algorithms equips programmers with powerful problem-solving skills transferable across virtually every facet of contemporary technology ecosystems. Their strategic importance cannot be overstated given increasing volumes processed daily worldwide. By staying informed about current advancements while building solid conceptual foundations early on, practitioners position themselves well to tackle emerging challenges, confidently knowing robust search methodologies lie firmly within their toolkit repertoire, ready whenever needed most urgently.